the weekly CFT colloquium. Today we have a pleasure of hearing the talk by Marc Aßmann. Marc is my collaborator in the Quant Era project, which we have just started last year in an international team of mixed quantum and theory and experiment quantum groups, and Marc is one of the experimental nodes from Technical University in Dortmund, Germany. Let me maybe briefly introduce Marc. He did his PhD at the same place, so also the Technical University in Dortmund. He did his PhD in quantum dot lasers. Then he did a postdoc at TU, and then he went to Gila, to Boulder, Colorado, for another postdoc. After that, he returned to his alma mater, to Dortmund, in 2014, and since 2021, Marc has been a full professor at the TU Dortmund. He is working, as you can see, in condensed matter, in solid state, or actually in polariton physics. And this is something that we are going to hear today, not only hear, but also see if the videos work. Marc, the ground is yours.
Great. Thank you very much for this kind introduction. And also thank you very much for inviting me here and giving me the possibility to speak here. So indeed, I will be talking about polaritons and vortices. And if you don't have any idea by now what it means, don't worry, I'll explain. Let me start with the most important stuff because I tend to run out of time. So let me start with the people who actually did the work. So we had a lot of collaborators, that's from the University of Würzburg and also from Princeton, who provided samples for us. We have field support from the University of Paderborn, from Stefan Schumacher's group and from Jan Sperling's group. And of course, the most important thing is, of course, the people who really did the work. So you see here, I pretend to know what I'm doing. I'm actually not. I'm happy that these people don't throw me out of the lab. But so Caroline Lüdes here built most of the setup. Yannick Müller is running it now and doing most of the programming. And my very talented postdoc here, Elena Vaschas, is basically taking care of all of it and explaining me what they're actually doing in the lab so I can talk to you. So as a motivation, why do we do that? You know that quantum technologies are omnipresent and everywhere with a lot of things, and there are a lot of different platforms in which quantum technologies realize. You know, quantum sensing, quantum computers, quantum key distribution, everything. There are a lot of platforms for doing that. Cold atoms are very well known. Yeah, superconducting qubits, at least from the circle, are well known. We have spin ensembles, or nuclear spins for memories. This is another task you need to do. We have cavities and all alike. Many of those are highly specialized systems, really good for one task. Yeah, atoms are great for doing quantum computing, or superconducting qubits are good for making large amounts of them. Photons are good for long distance, and so on. The nuclear spins are good for making memories, and so on and so forth. But what you see here is that the range of excitation frequencies you have and the range of coherence times you have vary over several orders of magnitude. So the problem is, it's great that we have plenty of platforms to realize individual quantum technologies, but we somehow need to make them talk to each other so that they are compatible. Yeah, no individual platform is really great for all things, so we need kind of interface between them. And the thing I will be talking about, polaritons, is a good light matter interface in that sense. So if you have never heard about it, this is a typical sample for polaritons. We are talking about excitons. If you don't know what that means, it's just an electron-hole pair. I was told we have people from astrophysics here as well. You can just imagine in the early universe when you have, protons and electrons and they form hydrogen, which is a neutral state. We have the same thing as semiconductor. You can put electrons and holes in there, and if you make it cold enough, they will also form a bound state of positive and negative charge, and this is the exciton. Yeah, so essentially it's the same thing. It's acts a bit like positronium. It's just not stable. And we put this in a cavity where we enclose light and basically wait for things to happen. So these things can be optically excited and they can decay, emitting a photon. And what we want to look at is the case when we put these things there, they decay, they emit a photon, when we absorb it, we emit it, we absorb it, we emit it, and so on and so forth. And if that happens, we're in the strong coupling regime, and as always, physicists are lazy and describe this just as a new quasiparticle, and this is called the polariton. Yeah, basically, it's a quasiparticle where permanently exchange energy between your semiconductor excitation here and your light field, which always goes back and forth. If you have a look at what's happening, don't be scared by the equations. This is just momentum space, and this is just the dispersion of this polariton. So this is the momentum, this is the energy, and as always, when you have strong coupling between two resonances, let's say two coupled harmonic oscillators, you could consider light as one harmonic oscillator, the exciton the second one. You get this splitting here, yeah, so you get mixed mode, and this is what it looks like. This would be the mathematical form, but what you should take along is this one has a minimum here. This is the dispersion, there's energy minimum. This will become important soon. Yeah, so just take this one part of the story, there's a minimum in energy space. So why should we bother about polaritons? The first thing is they are easy to study optically. Why? I told you it's a mixed particle of excitons and light, and we just confine it to a cavity. At some point, they will decay. The most probable decay mechanism is just that light leaks out of cavity, because no mirror is really perfect. At some point, some light will escape. This is directly a part of the wave function of this particle, and if the light escapes, you can directly study it to get some information about the particle. So it's really easy to study, because our optical signal directly tells us what's going on. They are light, because they are, let's say, at least 50% photons, so their mass is about 4 to 5 orders of magnitude less than the mass of an electron. They are bosons, so they are composed of different, so they are composite polariton. And what photons themselves cannot do, they interact with each other. This will also, again, become important. So as a loose analogy, I told you that in the early universe, you formed hydrogen out of protons and electrons. In a semiconductor, more or less the same things happen. You fill in electrons and holes, they form excitons, and these in turn, well, form polaritons at some point. And I told you in the energy dispersion, there's a minimum here. So they move towards the minimum. Now, I also told you that they are bosons. So you probably know how stimulated emission works in a laser. So if you want to have emission, the emission will become faster or stronger the more photons there already are in the mode you emit to. Here, the same thing happens. These things need to scatter down to the ground state, and the more polaritons there are already in there, the stronger this relaxation becomes and the scattering becomes. So when you have stimulated emission in lasers, you have stimulated scattering to the ground state here. So this is a bosonic effect, and basically this allows you to form a huge number of polaritons in this ground state, and this is then called a Bose-Einstein condensate of these Exciton-polaritons. The good thing is these are very light, so the critical temperature is much higher than for atoms. The downside is, well, this is not really thermal equilibrium. You need to be a bit careful because you permanently lose particles, yeah, because they always leak out of the cavity. It's a bit more complicated. But like 20 years ago, people have seen that it behaves like a condensate. This is real space, so a huge amount of occupation builds up in the ground state. And if you have a look at this dispersion momentum space, this is below threshold. And once it starts to condense, all of the polaritons end up in this ground state here. And this is what it looks like in experiments. So I told you it's somewhat similar to Bose-Einstein condensate with atoms. So I want to point out the similarities and dissimilarities. So I already told you what we have is a huge occupation of this ground state. So all of them, many of them pile up in this ground state. What you also have, what's known from VECs, is that you have coherence. If you don't understand what this picture shows, don't worry. This is below threshold, this is the condensate, and you basically just take this condensate and interfere it with itself, with a mirrored version. So if it's incoherent, there's no interference. If it is coherent, or if it's a macroscopic coherent state, this is a few micrometers here, you just get interference fringes, just like in atomic Bose-Einstein condensates. Yeah, you see the same thing here. What you also expect from Bose-Einstein condensates is superfluidity. Again, don't be scared by this picture. What happens here is we take this condensate, or we take these polaritons, and just send them, they behave a bit like a liquid, we send them somewhere, and send them against an obstacle. This is this point here. We just have it bounce off this obstacle. What happens? This is just a standard polariton, not condensed at all, just so it's scattered in all directions. And what you see here, this little pattern is just an interference between the incoming beam and the one which is reflected. So you get this interference pattern, and this is momentum space. So what would you expect for a thing which goes against the defect, it's scattered into all directions. And this is what you see here in momentum space. This creates the direction they move to, and you see this ring. So we just move all over the place and they just scatter from space there. Once you enter the condensed phase, it looks like this. You see there are no ripples anymore. And if you have a look at momentum space, they all just go into one direction and this ring has vanished. So basically there's no scattering anymore at this defect and they just flow past it without any real scattering. This is the equivalent of superfluidity. The final thing I will be talking about are vortices, and in these condensates also vortices form. It might not be totally convincing to you that this is the hallmark sign of vortices forming. Of course, you will not be able to identify this at the moment. That's fine. I will spend a few slides explaining to you why this strange fork you see here is a vortex, and actually, probably I should also explain what a vortex actually is, right? So we know that in PECs there are quantized vortices, which means in these Bose-Einstein condensates, if you want to rotate them, you can always only add angular momentum in quantized amounts. And this is how vortices form. I will show you. First, for the theorists here, the definition of what a vortex actually is. A vortex is a topological feature of a superfluid in a closed path around the vortex of phase undergoes a 2-pi winding. The superfluid flow is quantized. The vortex state is an actually symmetric ring of 2-pi phase winding around the vortex core where the local density is zero. Textbook example. Okay, this doesn't tell much, right? Maybe sometimes images help, so to put more simply, that's a vortex. Maybe that's it. Yeah, you might know it from above. So how do we find those features I mentioned here in this vortex? So what you have is a phase undergoes a 2-pi winding. It just means if you have a wave function of your condensate, this is the density, so the square root of it is the amplitude, and you have a phase here, and you track the phase by going in a circle, you have a 2-pi phase shift when going once in a circle. That's the first thing. You have an actually symmetric ring, and the vortex core below the density is zero. This means that the intensity looks like that. If you remember the vortex I showed you, you have a similar thing. So it just goes in a circle, and in the center, you have less water than outside. This is more or less a similar thing. You have no intensity in here, but here the polariton's just flow in a circle. And you have the superfluid flow is quantized. If you do the semi-classical analogy, how angular momentum is defined, well, it's R plus P, yeah, R plus P. And basically, this just means, well, it needs to go in a circle. Yeah, so basically this is how the superfluid flow is defined, so the angular momentum. And why is it quantized? Well, this is the phase, and if the phase difference when going through a circle is not 2-pi, you end up having problems. I'll show you that. What do we need? So basically we need a continuous wave function, right? Or at least a continuous thing when we go through a circle. We should not have any brutal jumps, otherwise, you know, it's not a good wave function. So what we need is a steady gradient and periodicity. This is not really obtainable in real space. So if you go full circle here and you want to end up at the beginning when you go full circle, you can always only do that with, you know, Escher can do it with optical illusions, but you cannot really do that. Yeah? There's no staircase which always goes up and you end up at the same point you start. Will not work. With phase, of course you can do it, because all functions are 2-pi periodic anyway, and there's no physical difference when changing the wave function by 2-pi. So if you just go full circle here and have it changed by 2-pi or 4-pi or 6-pi or 26-pi, whatever, you have physically again the same situation, and this works. Yeah, so basically this is what governs here superfluid flow. If you have a look at it, this is now the phase encoded in colors. So this is 0. This is pi, and 2-pi and 0 is again the same. You just see that your phase varies by a certain amount when you have a look at the wave function and go full circle. It can either be 2-pi or 4-pi. Could also be -2 or -4-pi. So the rotation direction is more arbitrary. You can rotate it the other way around. Yeah, and you just see this is basically more orbital angular momentum. And for more phase shift you have, the more orbital angular momentum you have, which is here denoted by the typical quantum number L, which you would also use for hydrogens. Yeah, so this is basically your angular momentum quantum number. And the stronger your phase shift is, the larger your angular momentum is. Maybe keep this one in mind. If you have a look at atoms and you take a BEC of atoms, put them in a bucket and just try to rotate the bucket, and try to, get angular momentum into the system, this is exactly what's happening. Yeah, so I told you the superfluid flow there needs to, or the angular momentum needs to be quantized. And what actually happens is that vortices form inside this BEC of atoms. And people who do atom physics really had a look at it, and this is what they see. So they really see an ordered array of these vortices forming. And the way they see it, as I told you, there's a density minimum in the middle. And this is exactly what I can see here. So it's, of course, incredibly difficult to see the atoms flowing out. BEC flowing in a circle, but what you can see is this density gap in the middle of the vortices, and you really see lattices of these vortices forming in an Bose-Einstein concept of atoms. Yeah, and basically you have tiny mutations, tiny vortices here, and all of them flow in a circle.
Sorry, can I ask? So,
Yeah.
like those minima of densities, like, do you have like a? Can you infer presence of vortices of the phase just from minima of densities? Because like, do you have direct access to this information?
It's a bit more difficult. Yeah, typically you would also have to measure the phase. So you would have to do interferometry. This was done in atoms. I'm not an expert on that. I think a few years later, so not in 2001 certainly. I will show you later, but in our system we have direct access to that. But
So it's just an indication.
Here I would say at this point it's just an indication. Yes. But I can show you in our system we have that. Because the next question is, of course, how to observe this in our system with polaritongs. I told you it's similar, but how large is the similarity? The good thing for us is light, which really leaks out of a cavity, is directly a part of the wave function. So we can play games with light which leaves the cavity. And there we can directly measure the phase. This is our flow. Yeah, so when the light leaves the cavity, so we can measure the photon energy, and this tells us about the energy of our polaritons, for example. We can also measure the polarization of our photons. And this gives us information about the, well, it's called pseudospin, but basically about the polarization of the polaritons. There's a small difference, but this is for the experts only between pseudospin and polarization. For the audience, it might be good to consider the same. If we measure the phase of our light field, we directly get information about the phase of a condensate. So we can indeed measure the phase, that's good. And, well, if there's vorticity, so we have vortices in our condensate, the question is, what signature would we find in our light field? Therefore, these the one-to-one correspondence is quite easy. Thinking about quantized orbital angular momentum in light fields is not exactly that trivial, but it works. If you go back to 1992, Aßmann here already found out that even standard light fields can carry orbital angular momentum. By this, he doesn't mean circular polarization, but really orbital angular momentum. I'm not sure how many of you know about that, but it's quite easy. So it's the same. What you need is a light field where, if you have a look at it, the phase, when you go in a circle, yeah, you have a plane where the light field propagates, and you have a look at the phase in this plane. It just needs to do a full 2 pi rotation, or 4 pi, when you trace it in a plane. What does this mean? If you consider what the pointing vector means of a light field, so this is a propagation direction. It's typically perpendicular to planes of constant phase. This means if you have a phase gradient, it just means your propagation direction at each point is slightly tilted. And basically, your light field then looks like that. At each point, it's not propagating straight, but at a slight angle, so it's slightly tilted. And if you really propagate it forward and calculate the interference and how it propagates, you will find out what you get out is a so-called Laguerre-Gaussian mode, which is interestingly shape preserving. And these are the wings you might have seen. So if you have seen wings as light fields, this is how they are created. And basically, really, they can propagate, and well, the pointing vector is indeed rotating in a circle. So then the light indeed carries orbital angular momentum in that sense, but you have well, the analogy is a bit, but it's a rotating light field in the sense that the pointing vector is linear. Yeah, you can have it. So how to do spectroscopy on this orbital angular momentum, as you correctly asked. So you can have a look at whether these vortices form in matter and wave interferometry for atoms. Then you see that there's a quark here. It basically means if you have this 2 pi phase gradient and you interfere this with a linear phase gradient, what will come up is strange quark-like intersection. Just accept it for the moment. Yeah, if you visualize it, if you do the math, it works out. Optically, we can just do the same. We can just take our emission, send it to a beam splitter, cut it into 2, and kind of put it to a mirror which just reflects it, it turns it around. So basically you get, you know, an upside down copy of your light field and interfere that and have a look at what happens. If there's no vortex, you basically just get this very boring linear interference pattern, nothing much happening. If there is a vortex, you indeed see again these forks. And this is typically really the hallmark sign that where a vortex is inside. You see, if you have a spatially solved phase pattern, you see these forks appearing. And this is essentially how you can identify it. You need to have a look at the phase. Also, if you're maybe familiar with more complicated physics, you know that there are BKT transitions and like that vortex anti-vortex pairs may form, which just means that if you have a vortex going this way and a vortex going that way, they tend to stick to each other. This you can also see by having just two similar forks next to each other. So this is the opening fork, this is the closing one, and this would be just a pair of two vortices with opposite directions. As you asked, so how can one do this? What one really does is spatially solved interferometry. So you get an interferogram of your emission and you have it spatially solved. So these are about 12 micrometers here and there. And this is what it looks like. This is this fork. And from this interferogram, you can get the intensity or amplitude and the phase of your light field. This has been done already in 2008, for example, Konstantinos Lagoudakis here. And if you have a look at the intensity, you see at this point, you indeed have zero intensity. So you have a dip in intensity. And you have a 2 pi phase gradient if you go around here. You might not see it directly, but if you just plot it, you see that really you have, well, it's not an exactly linear gradient, no system is perfect. Yeah, but you really have a 2 pi phase shift when you follow the circle. And these are just different radii, and see on all of them, you have this 2 pi phase shift. So you can really identify them by optical means. Now, our idea is to make this to a light matter interface. Can we kind of create them or control them? Because one of the, well, I don't want to talk about qubits because in polaritons is a bit, but one interesting thing is with superconducting flux qubits, we use these vortices to carry information. And just as the toy model, we would like to understand, okay, can we do the same? So can we, for example, if we have a vortex, can we control, if we create it, which direction it will spin? This way or that way, and can we even probably switch its direction? Can we make it, if it's going this way, can we have some means to make it go the other way around? So this is our rule starting thing. So classically, it's quite easy to form a vortex. So there's a thing in classical fluid dynamics called the Reynolds number, which is again, when you have a fluid which flows against a defect, just kind of tells you what will happen. So are you in the turbulent limit or in the laminar limit? And then this Reynolds number, we have essentially just 3 things entering. So if your liquid flows against a defect, how large is the defect? How quickly or how fast is your fluid flowing? And this is the kinematic viscosity of your liquid. This means, well, is this air, water, or honey? So honey has a high viscosity, air, very little one. So if you have a look, you could, for example, consider a rather small defect, a slow velocity, but a rather viscous liquid like water, and then vortex formation, which would look, for example, like that. Yeah, this is a classical example. The duct is now the defect, and the water flows against the duct, and you see this typical wave you see for ducts, bones, whatever. You can also go to the other limit with much higher velocity. Yeah, and well, a larger defect, this would be, for example, what you see in airplanes. So this is the vortex research facility of NASA, and you see that here vortices are formed. Of course, this is a standing picture. The dynamics are a bit more interesting. So we would like to know how these vortices form. So I brought a video. Maybe it's working, maybe it's not. Yes, it is. So this is a test airplane, and basically you see how vortices form when it goes against the defect. Yeah, so basically this is how it is. You directly see it forming back.
Nice.
So, and our idea is now, okay, for us, vortices form too, but unfortunately a bit faster. So it's rather a matter of picoseconds compared to seconds here. So the question is, how can we investigate this? Don't be worried, don't be scared. This is taken from a paper. I'll briefly walk you through it. We just again do the same thing. We call it interferometers. And then we use these to have a look at the intensity and at the phase. This time it's just time we solve. So in the middle, you have interferogram. The green thing here is a defect, and basically we just have this polariton liquid, this condensate, which comes from the right-hand side and just crashes against this defect. So what we have is, we come from the right-hand side, crash against this defect, and with time, so this is before the impact, and then time increases, in red vortices form, and you can follow it. There you see you have here this 2 pi phase gradient. Here you can see quite well at about 5 picoseconds, and at the same points you have a minimum in intensity. Yeah, so this is basically what I want to look at. I also brought a video from this publication. Don't be worried if you cannot directly see it, but this is at 0. Now the impact comes on here, vortex forms. You see this 2 pi phase gradients, and then it just decays over time, it moves out of the image. I understand that this is a bit noisy and hard to understand, but just have a look at here, the vortex is forming. You see this 2 pi phase gradient. For the experts among you, fine. You might know that I'm talking now about BECs, but we are basically having a 2D system. So we're talking about quantum wells, just confine excitons on a 2D plane. And you might know that there's a Mermin Wagner-Hohenberg theorem that essentially says that there's no BEC in 2 dimensions at finite temperatures with this time equation. Yeah, that's true. However, essentially because vortices will mess it up. So there's no long-range coherence because these vortices will form. There's little energy transfer and they will just mess up the condensate. However, some of you might know that there's this Brzezinski-Kosterlitz-Taurus transition, which kind of saves us so that we still have long-range order. What does that mean? Typically, it's quite cheap energy-wise for these vortices to form. They may form spontaneously and they mess up your phase. So basically, they really make a system pretty incoherent. So what now may happen is, okay, these may form, but as I told you before, there are vortex and anti-vortex pairs. One going left, one going right. And if they meet up, kind of, it doesn't really mess up the phase as badly because we have this one for opening, but closing again. So basically your region where your phase gets messed up is confined to the small region where vortex and anti-vortices meet. And besides that, it's fine. So you still have at least a quadratic product. And this is what happens if you do what I just did. You follow a lot of vortices after formation of condensate and you just mark them. And black dots are a vortex going this way. Red dots are vortex going the other way. And you see after some time, they just tend to meet each other, as you can see here, and annihilate. Or at least flock to each other. And this kind of saves your condensate into D. So in our system, we indeed have something similar to a condensate in the sense of this transition. Now, as I said, the question is, well, can we utilize these vortices for something and can we switch them? A good thing about our condensate is that we can create it optically. We just shoot a laser at it and create particles, electrons and holes. These polaritons we form see these particles as well. Yeah, so they are like, it's basically as if you have hydrogen, they see free electrons and protons, there would be an interaction as well. They are neutral, but that's still there. Here it's the same, and the interaction is repulsive. Actually, that just means whatever way we shape our pump spot, the shape of this pump spot is simultaneously a repulsive potential for the polaritons. Yeah, so basically, if this is our pump spot, so we have a loose spot here, a little opening here, and another, well, curve here, then the polaritons will just form in whatever is left open in between there, in this ridge, yeah, and they will just form in there. If we have a shape such that we open up a curve here, the polaritons form in the curve. Of course, the interesting thing for us is, well, why not do a wing then? Yeah, we have a wing, and then the polaritons can just sum up or accumulate in the middle of a wing. This is what we would like to look at. Why a wing? Well, if you have a look at your bathtub again, it's extremely unlikely that, if you put things on a wing and want them to toss inside, that will just go like this, but many of them will go this way, a bit in that direction, will circle. Okay, this is what you might know from the bathtub, or if you from roulette or whatever. Yes, so basically you have them going in a circle, and this is directly how vortices may form here. So they just form inside, and they may form, well, like small fluctuations either go that way or that way, and they will typically start to flow circling. Yeah, so we would like to investigate, can we now trigger which way they will go, and can we switch their rotation direction? Well, We can just monitor how we flow in. It's easy. The question is, how can we well, change the direction? Actually, it's quite simple. I told you already, each pump spot we have is simultaneously a repulsive potential. So the easiest thing is, well, the polariton flow in there and they flow in a circle. If you just put another pump spot in there and just make a question to this pump spot again, they question to an obstacle, and they are basically reflected. Yeah, and if this happens, they move in there, crash in there, are reflected, and then by the next time they come to this obstacle again, have removed this obstacle again, we effectively have reversed the direction of flow. It's in a really classical picture. Yeah, so it's not easy. So really, we have the flow against there, put the obstacle there, we crash against it, are reflected, we take the obstacle out again, and this is really just what we do in order to, really reflect it here. This is what the orbital angular momentum we see. As I said, we need to trace the orbital angular momentum of our light field. Yeah, so this is really what is supposed to happen. So we have a right circularly polarized or right circulating vortex, which is +1. If it goes to the left, it's -1. Here we put, let's say, our obstacle, and what happens is the orbital angular momentum and the vortex starts to change and starts to oscillate back and forth. Yeah, so just go. And if we just remove this obstacle at some point, it hopefully just stays with it. This is what our theory colleagues calculated. Of course, in experiment, it's a bit more non-trivial. Yeah, they also gave us some hints on where to look. So basically, they told us, okay, how long do you need to make the pulses so that you can really switch it off and so on and so forth. We tried to follow that, and we came to the problem of, okay, we want to identify the orbital angular momentum. How can we identify this in light field? So basically, yeah, how can we do spectroscopy on it? We would need a device which tells us how much of a helical phase gradient we have in our light field. Yeah. Fortunately, and we need to sort our signal according to that. Fortunately, we already have a very highly regarded quantum optical device that does the same for linear phase gradients. So there are optical elements which, when you put light fields with linear phase gradients onto it, sort the output according to the linear phase gradient. It's a lens. Yeah, basically, think about it. If you go to it, it's focused to a single spot. If you go on it with a different angle, this is just a linear phase gradient. If you put it on axis, it just gets focused to a different spot. That's it. It sorts linear phase gradients to individual points in the back focal plane. So basically, all we need to do is take our light field, where we have a helical phase gradient, kind of cut it open and transform the helical to a linear phase gradient somehow, and then we can just use the lens. That's kind of a strategy. Yeah, so we need something, we have our helical light fields, and basically we want to sort them so that we can distinguish them. This is indeed possible. What we need is a so-called spatial light modulator. This is a phase mask. So we just need to put our light fields onto a phase mask, which transforms the phases. And basically this thing, if you have a phase mask like that, it just cuts it open and it stretches it to a linear phase gradient. Of course, you introduce some errors which need to be corrected, but if you do it like that, you really can get a linear phase gradient out of the helical one, and then you can sort it on the detector. Yeah, let's say things which circulate to the left go here, to the right go here, no OM go here, and so on. And we can put it on a detector of high temporal resolution, which can be picosecond resolution, and then it looks like that. This is like, say, the spontaneously building vorticity. So this is, let's say, right circulating, left circulating. You have a certain asymmetry. Here we put this obstacle in, and if our pumping is too weak, nothing much happens. If it is right, has the right intensity, you see that this becomes more intensive, yeah, and this becomes weaker. So we indeed can switch. So basically, this is the sign that we really were able to, let's say, counter the rotation direction. And if we use too much power again, it doesn't work again. But there is a certain region where we can actually switch the direction into which our vortices are rotating. Here's unfortunately some pictures are missing, well, whatever. The important ones are there. So what else might polariton be good for? I told you it's a good light metal interface. Okay. So we can build optical couplers, transistors. If you want to go to room temperature, you can have perovskite microcavities to go to high temperatures. You can also put neural networks out of it, but you have more experience here in place than I do. So just ask your own people about it. They're much better at it than I am. So, yeah, but I told you the interesting stuff is about being a light metal interface. So how much if we really pump these hard laser pulses on, so how much does this cause any decoherence? Yeah, we have a lot of free carriers which are typical to the system. This should, be detrimental. Unfortunately, it is. What we tried is we just put polaritons somewhere, superpose them with such a potential which is anti-trapping, so that they just flow away, and have a look at, well, how much intensity noise do we have at a position where the potential is and far away from it. We just checked it. This is the second order for our correlation function. This is basically just a measure of intensity noise. The higher the value above 1, the noisier the signal is. So this means directly at the potential it's quite noisy. Far away from it, it gets better. So yeah, decoherence is a problem. However, we would be interested in finding the dynamics of this because we are on the microsecond scale. We want to be fast. Yeah, so I'll briefly walk you through it. So the method we use is homodyne detection for doing this. Basically, this means we do not measure intensity but fields. How can you measure light fields? It's quite easy. We again need a very highly technical quantum optical device, a beam splitter. And we just take our signal and superpose it with a local oscillator, which is just a strong coherent laser field. Fortunately, conservation of energy is a thing. This means that the light field you get out on the one side is just the sum of both fields, and then the other one is the difference of both fields. Well, if you just put detectors here, measure the intensity, you get field A plus field B squared, field A minus field B squared. And if you electronically just subtract these things from each other, everything which survives is a mixed term. The others are just subtracted, and the mixed term survives, which means you have a weak signal, which is amplified by the magnitude or the amplitude of your strong laser signal, which is applying here. So you're really able to measure quite weak light fields because you amplify them with a well-known, well-characterized laser field. You can really measure fields. And the good thing is this local oscillator also acts as a filter because it only interferes with signals which have the same polarization, spatial mode, temporal profile, and so on. So basically, if you use a short laser pulse for a photosecond here, the time resolution is also 100 femtoseconds. We now try to determine whether we can determine the photon number noise rate. This has already been done in the 90s, fortunately. We just needed to take the equations and plug things in here, which is good. So we can get G2 from it, these photon number correlations. Why should one do it? So people have done this before with typical intensity correlation measurements. If you've ever done some like that, it takes a few minutes at least. If you have faint intensities, it can take up to an hour or more. The way we do it, we just need to collect all of these amplitudes, and you need about 100,000 to get a single value. It sounds like much, but the typical laser repetition rate we have is like 76 megahertz. So basically, for a single measurement, we need about a millisecond. So we can take 1,000 of these measurements per second and time check all of them. It's a lot of data, 5 gigabyte, okay, but we can indeed real-time time check these G2. So we can directly follow, okay, this is just a laser which we tested and we made it unstable on purpose. And you see if a photon number here in red is jumping, these photon number statistics, the noise is of course also jumping, and we can follow it with millisecond time resolution. And that typically you need at least minutes, if you do it done at intensity. So this is nice, so that we can really follow these noise dynamics in kind of real time. We went a bit further. This is also just for the experts. We just did 2 channels so that we can measure field, longer cosine and sine components simultaneously. When you get a ring like that, you can really imagine this like this is approximately the light field you have in amplitude and phase. Yeah, and you see if we make it noisy, it jumps above and below threshold. Below threshold, you just have a thermal cloud here, and above threshold, you have something which looks like a thermal light field. And you can also see that the intensity noise behaves accordingly. So if you have low intensity, noise is huge, and vice versa. This is already good. However, we wanted to investigate how much of the light matter interface we have, where it would be good to understand what we actually measure here. So with G2, if you have a look at the density matrix of your light field, so having bit complicated, I hope density matrix is still fine. It's just sensitive to the diagonal matrix. So it is just intensity noise. If you want to have an interface, you would also want to have a coherences, so superposition staying alive. This is something which G2 doesn't quantify at all. Yeah, so we would like to have some quantifier which is also, let's say, sensitive to these off-diagonal elements. That's okay. There's a different quantifier which is called quantum coherence, and I'll very briefly introduce to it. Mathematically speaking, it's quite simple. We just take the off-diagonal matrix elements, take the magnitude squared, and sum it up. That's it. So you can also Why is this? So it's the distance between a density matrix and the closest completely incoherent density matrix. If you don't understand what this means, this would be the density matrix on Fock space, so photon number of a coherent light field. And if you make it incoherent, you just delete everything except the diagonals, and this is what it looks like. So essentially, you just need to measure the distance between this and that's coherence. Yeah. For the experts, we use the L2 norm as a quantifier. You can use different things. If you do this, you can calculate the quantum coherence by measuring the Q function I told you. I don't want to now overburden you with this quite complicated formula, but there are only two physical things in there. Alpha naught squared is just your coherent photon number, and bar is just your terminal photon number. That's it. So basically, this reflects in the amplitude we see here of the light field and the width of the wing. So amplitude of wing, width of wing, we can measure that, and then we can determine our quantum coherence. Does this help? What we now do is we take our Polariton condensate and just increase the pump power. Below some threshold, it should be terminal. Above, it should become coherent, and we just want to check what's happening. This is the terminal photon number, this is the coherent one, and we just want to see what happens above threshold. This is the ratio of both. You see it becomes way more coherent here when we enter the threshold. This is the second order correlation function I showed you, which is just sensitive to the diagonal metric. So noise is large below threshold, and it directly goes to 1. Above threshold, it stays there. Perfect. This is what you want to have. Now, if we have a look at quantum coherence, it's a bit different. Yeah, so it's totally incoherent below threshold, that's fine. Coherence-wise, it's drastically on threshold, that's fine, but then it decreases again. This is something you don't see here. So in the last, if I have like 5 minutes left, yeah, maybe 2, I'll hurry. I'll walk you through an explanation of why this is the case. I gave you this definition of quantum coherence, which you can also write a bit differently. This is just the trace of a density matrix squared minus the trace of a density matrix of this incoherent state squared, which is, if you go back to your basic quantum mechanics lecture, this is just the purity of your state. So is it a pure state or is it a mixed state? Yeah, so if it's perfectly pure, this will be 1. And basically, this is just the difference. Now you can think about, does this give us some method to quantify or some limit? There are physical quantities which also include the purity, for example, the mixedness, which is quite trivial. So basically, the mixedness is just 1 minus the purity. So if you have a very pure state, it's not very mixed. If you have a very mixed state, it's not very pure. This is kind of trivial. Yeah, so these do add up. So if you add up all of this thing just falls out, but this one stays in. So this really leads a very simple formula, which is that your coherence plus your mixedness plus, this is a bit complicated, this is the purity of the incoherent state it dephases to, just add up to 1. That's quite simple. Okay, mathematically speaking, yes, but that should tell us something about, our system and about lasing and about why quantum coherence behaves so strangely. I set up a really, really simple toy model for condensation and also for lasing. This is so simple that it's basically a class term. So how does lasing work? You start with vacuum, which is just a Fock state 0, no photons, nothing at all. If we have a look at the 3 quantities we have, well, vacuum obviously does not have any coherence, just 0 photons. Also no mixedness, it's a pure state of 0 photons. So if you dephase it, it stays with vacuum, but it's a pure state. So this third thing is 1, and everything else is 0. Now, how does lasing work? If you start a laser for vacuum, basically you first have a bit of spontaneous emission. The occupation of the lasing mode builds up, and at some point you have stimulated emission taking over, and yeah, this is. So first, let's do a toy model for the spontaneous emission. This essentially means you get a small terminal component which builds up. Yeah, this is not coherent, but spontaneous emission is really term light. So what happens is this is actually a mixed state because terminal light is always mixed. Yeah, so you get a bit of spontaneous emission, you get a bit of mixedness, and if you dephase it, it still stays with terminal state, so purity of dephased state changes too, but basically all that happens is you add a little mixedness. Now, how does the onset of lasing work? Yeah, basically you just take the state and coherently displace it. You have a unitary coherent displacement, you get a real amplitude, and this is how lasing works. Very simply. Devils in detail, it's more complicated. But the interesting thing about these unitary displacements is they do not do anything about the mixedness. Cannot change it. If it was mixed before, it will stay mixed. So this essentially means you get some coherence. The mixedness is as it was, and yeah, this purity of the dephased state, whatever is this. The important lesson from this is whatever your coherence is, it is limited by this initial bit of spontaneous emission. However much mixedness, however much thermal component you had initially, you will never get rid of it. If you do the math and see how it depends on the thermal photodynamic, you see this mixedness is something like that, and it depends only on the thermal photodynamic, as you can see here. So this means essentially any bit of thermal emission you have beforehand is detrimental and limits the coherence you can actually gain. This also explains why quantum heaps drops again above threshold, but G2 stays constant. This is a relative measure. If a relative number of coherent photons to thermal photons increases, this will get better. Better here means closer to 1. In our case, we have a hard limit, and every single thermal photon degrades it. So if you go further above threshold, we always also have a tiny little more bit of spontaneous in infinite node. So the total photon number goes up, the coherent fraction also goes up, but the absolute amount of thermal emission also increases slightly, and this decreases our coherency. Yeah, basically, it's really just the absolute number. It's not relative, it's really absolute, and this is what kills us here and makes us go down again. I have 1 more minute. I would also tell you why this is important, or why this is useful. I told you this is for quantum technologies, and one of the easiest tasks we can do, I mean, I'm talking about condensates or lasers. This is a perfectly classical light field. What task can it have in quantum technologies? Well, you can at least initialize qubits with it, for example. Yeah, if you have Rabi oscillations, you have a two-level system and want to drive it to the excited state, or you want to drive it to a superposition state between ground and excited state, yeah, you will just go resonantly to it and drive it to the state you want to initialize your qubit in. Yeah, so the question now is, if we have quantum coherence, or if we lack it, does it make any difference? So I'll just plot here my two-level system with the probability to find it in the excited state. Using the state of quantum coherence, you see perfect Rabi oscillations. Nice. And now if you use incoherent light field without, so we just kill the off-diagonal matrix elements, let's see what changes. Nothing. That's a bit disappointing. I know. However, if you're a bit into qubits, you know that just the probability to find your system in the excited state might not be the only thing you're interested in, but you might also be interested in what kind of state this is. So if you instead have a look at the purity of a state of a two-level system, you will find that if you have a coherent field and you go to, let's say, superposition here, you are still in pure state, while if you see here's purity of a two-level system, it goes down to 0.5, which means it's a mixed state. If you have an incoherent comp beam and try to drive a two-level system, you do not end up in a pure state, but it's a mixed state, which is at 50% probability of down, but nothing you can use a qubit with because it's not a superposition state, but it's a mixed state. Yeah, so this is indeed useful in that sense. Yeah, this is a huge difference, and for quantum technologies, it's really important. This is indeed a quantitative metric. I simulated this here for different photon numbers, and you can still see, as to crank up the ratio of quantum coherence to mixedness, you will get a better atomic purity at this superposition state you want to create. Yeah, so this is just a purity, this is a mixed state, this is the superposition you want to create. So minimizing this mixedness seems like a reasonable overall design goal. As a very last thing, well, if you want to optimize it, can we do it with our Polariton condensate? Yes, we can just use the same strategy we had beforehand, use rings and make sure the Polariton forms somewhere where there is no potential. And if we do that, it looks like that, momentum space, real space, and if you do that, you see the coherence really goes up. We had 0.2, and now it's 0.6, and it does not degrade if you can't use strong. Yeah, that's good. So I hope I did not take way too long. Okay, it's fine. So how much is, I hope I could convince you that Polariton system that at least interesting is like meta interface. Yeah, so this is what I would see them. I'm a spectroscopist by trade, so I hope I could also convince you that this homodynamic spectroscopy is part. For us, it's really important. Yeah. So, and I hope I could also convince you that quantum coherence, although the name is very quantum, is meaningful also if we study classical light physics. So, what will we do next? I told you, some spectroscopists being fast is important for us. What we did so far was having a look at this G2 and its density matrices, and we needed to reconstruct all these 5 gigabytes of data in due time. It takes time. Where we really want to go is to do this in real time so that one can readjust on it. Yeah, you can have a look in the lab, you can look at the data, and you can really have real-time adjustments on what you see. These are our first tries, so these are really videos taken in real time. This is G2 when the laser is cranked up, and this is the density matrix in Fox space of the displaced coherent state, or the displaced thermal state. You just crank up the photon number, and these are really real-time constructions of density matrix, and this is where we intend to go. Yeah, and with that, I hope I've not taken too long. Thank you very much for your attention. I'm very happy to answer.
Thank you very much, Mark, for the exciting talk. Questions? Michał, please.
Thank you very much for a nice talk. I have a question about this model of quantum coherence. I'm not sure if I understand it well. So I think that normally this dependence when you get higher coherence above threshold and then it falls down, it has been investigated in the past quite a lot. And usually the explanation, like hand wave explanation, is that there are some non-linearity interactions and it leads to the phasing of the numbers.
Yes.
So I understand that you are proposing some other explanation based on the let's say, initial state before condensation.
And these two things are not mutually exclusive. So indeed, there are a lot of nonlinear things which make things worse. I'm quite explicitly referring to a situation where you see this coherence in, let's say, our measure, but you do not see it in G2. Because if you have this non-linearities, you typically also see it in G2. We can also create situations where that is the case, indeed. So if we increase the detunity, it becomes more positive and with more oxygen external interaction. Then we indeed see both of them will decline. That's true. That's absolutely correct, yes. What just piqued our interest is that there's this situation where G2 doesn't seem to care, but here we see it. And in this case, I would assume that if we just have a different quantifier here, it's really very sensitive to the absolute time of photon. So it's this very limited scenario. That's true. There are other decoded mechanisms which influence both.
Okay, thank you.
Okay, anyone else? From the online audience?
No.
No. Okay, then I would have a question. So, just a very naive question. So, how come that the condensate flows? You've been using this verb all the time and showing an obstacle. So, actually, I would have two questions. So, how do you form an obstacle? And how can you understand maybe the hand waving way why the polariton condensate behaves like a fluid?
So let's start with the easiest thing. What makes the defect? How can you introduce one? So one thing we did was just putting a pump spot there. It's one possibility, but the thing
you mean that there is a laser pointing at some point?
Possibility, but historically it's been way easier. So if you create these samples, they are quite large, so millimeter or even larger, and they are never quite perfect. So you work on via MBB layer by layer, and usually it's never perfect, and there might be some stacking defects or other faults, and you never work on perfectly. And this is the easiest way to form a defect. So you must got your sample for a position where the sample growth did not work that well. You have localized inclusions of something else, for example, and you just use this. This is perfectly fine. This is what your periodic order is. Why does it flow? There are two possible responses to that. One thing you can do is to make it flow on purpose. Let's go back to this way here. So this was our dispersion, and this is momentum versus energy. And one thing is, I very often showed you non-resonant excitation, so these form spontaneously. What you can also do is you can directly create them resonantly by making laser resonant with this dispersion here. And you can also shine a laser at an angle when you are directly resonant with this one, and then you can directly put it in with the momentum you want to have. Or the other thing we can do is this puzzled in the very early times of polariton condensates, this puzzled people because they always saw all kinds of momentum. This was only later understood that, as I said, the pump spot also acts as a repulsive potential. So what happens if you just use a Gaussian pump spot, which is standard, the polaritons form there, see the Gaussian pump spot, and we just fall down the Gaussian potential, and then just keep on moving. Because this is a repulsive potential. Once we are away from the pump spot, this potential energy has been converted to kinetic energy, and we need to move somewhere. So this is the outcome.
Okay. Thank you. So you can buy this card and also use it. Thank you.
You mentioned that the interaction between the vortex is repulsive. So that is related to the angular momentum, or?
With the vortices, it's a bit more difficult. This is between the vortices, it's not necessarily repulsive. I think these guys studied it in detail. I'm not exactly sure. I think it is attractive between vortices with different rotation directions, but repulsive with the same. But don't quote me on that. I would have to read it up, and I'm not perfectly sure whether as a huge parameter space, whether it's super parameter space.
Actually, what is the time scale here? From I understand it goes from the high concentration to no vortices. So what is the time scale between the initial picture and no vortices?
We typically have a look here at something in the pico to nanosecond range. From picoseconds to at most few nanoseconds, because the cavity lifetime is usually short. These samples, for the best samples we had, can go to 100 picoseconds, but usually it's shorter. This is the typical time scale.
Okay. So it's fantastically rich physics in such a short time scales. Very nice. Any more questions? Regina.
So, can you observe fringed cat kind of structure in vortices, superposition of clockwise and anti-clockwise vortices?
So I didn't get the beginning, so.
Do you observe cat states in vortices?
Cat states. So far, no one did. Let's put it this way. I'm not aware of anyone who did. But I see where you're going to.
It's like superposition of two opposite to.
Yeah, well, I mean, similar to I think right. I wouldn't know how to quantify that it actually is a cat state and lots of things, but sounds like yeah. I will see it. So as far as I know, no one did.
Okay, anyone else? Yes, please.
So understanding these vortices are like topological defects or whatever. So switching the sign of the vortex seems like very non-trivial thing to do. Is it an interesting thing to look at the dynamics of the fluid after doing this vortex switching? Does anything interesting happen? Or if they have a fluid with paired vortices, when you switch one of them, what happens?
Yes, this is what people have kind of, proposed, especially our colleagues from Paderborn. So what we would love to have is, let's say, several rings next to each other, where you can well define and have, things between vortices flow this way and that way, and see what happens if you change the flow direction, what happens to the other ones. So far, getting the samples for that is a bit hard because we really would need to lithographically define it. So we are always optically imprinting things. This works for a single vortex. We haven't really managed to get coupling vortices. Some people try to, I forgot who it was, try to have, let's say, box vortices, so that they have, let's say, a small vortex in here, a larger vortex on the outside, and but this is also not what we are able to do. We are at some point maybe try to convince our sample girls to grab something like that and look at it. But this has been proposed. I fully agree that it would be interesting at the moment for us. It's experimentally out of reach, but we would be interested. Yes.
Okay, anyone else? If not, let's thank Marc again.